One of the things that's also really impressive about this project is an enormous amount of software and hardware was developed on schedule and in the budget of the project as it was originally envisioned. And so that in itself is pretty impressive when you think about so many other projects in other areas where they become very expensive and take much longer than originally planned. So I would say that Frontier is coming out about when I expected. It's funny you should ask. So there is a proposal for a new college, and it's called the College of Computing, Data Science, and Society. It's certainly a challenge. There is competition also across the universities as well as with industry, as you pointed out, for talent. And that's faculty talent. It is also attracting graduate students and postdocs beyond Exascale. And that's because data is going to stream from the instruments into the supercomputers, and that you want feedback.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you again.
Great to be with you. We are here for the big Exascale Day.
Yes, this episode will, to some extent, be focused on Exascale, and we have the pleasure of welcoming Kathy Yelick as our special guest. She is the Vice Chancellor for Research and the Robert S. Pepper Distinguished Professor of Electrical Engineering and Computer Sciences at the University of California, Berkeley. She is also Senior Faculty Scientist at Lawrence Berkeley National Lab. Kathy, it's a real pleasure to have you with us today.
Well, thank you very much. It's a pleasure to be here.
Okay, why don't we jump in a little bit on the Exascale front. With the Frontier system delivered at Oak Ridge National Lab and Exascale certified at least by the top 500, we're very curious about the Exascale story as you saw it and participated in it.
Well, I've been involved in Exascale really from the beginning when there were early reports, meetings, town halls put together to talk about what could we do with Exascale computers that we couldn't do at the time. And I think what's really exciting to me about this Exascale program that DOE has had, the Exascale initiative, is the combination of really unique applications that can use Exascale computers to solve new scientific problems and provide new scientific and national security insight. That combined with the software and then the hardware, which was developed in partnership with industry, to me, what makes Exascale really exciting is those capabilities.
While there is clearly some national security objectives for this project, what should we expect to see in terms of the kind of impact that is visible to the population as a whole, not just specialists?
There are over 20 applications for basic science problems as well as applied energy problems in the Exascale application portfolio. And they run a gamut from very traditional sorts of HPC problems, such as climate modeling to help us really understand and make predictions about what will happen under climate change. And these applications now have new capabilities, new features, but also applications such as the one I'm working on microbial genome analysis, looking at 100 terabyte data sets of microbial data. There's one on cancer and using machine learning for cancer. There are things looking at wind technology as alternative energy sources, and just an enormous portfolio of really interesting applications that I think will benefit society broadly.
Yeah, I know, for example, you mentioned energy research. And one thing I've heard along the way is that, say you take the fusion problem, a system like Frontier can just incorporate and take on either the entire fusion problem or a much bigger part of it than previous supercomputers. It's that kind of thing that Frontier can do, right?
Absolutely. Frontier is going to allow us to look at what we call multiphysics problems in the industry, which means that things that we used to just look at, for example, the fluid dynamics or the mechanics or the electrical properties of various systems, we can now look at all of those things in combination.
I'm just curious, were you surprised that at least Frontier has crossed the exaflop barrier when it did, or did you think it would come earlier? What about the timing of all this, especially given how long you've been involved in the Exascale project?
Yeah, I guess I was watching the timing more carefully when I was in a management position at Lawrence Berkeley National Lab. running the
Hmm.
computing sciences program there. I think this is roughly the time frame that I was expecting. It is aligned with the project schedule. One of the things that's also really impressive about this project is an enormous amount of software and hardware was developed on schedule and in the budget of the project as it was originally envisioned. And so that in itself is pretty impressive when you think about
Mm.
so many other projects in other areas where they become very expensive and take much longer than originally planned. So I would say that Frontier is coming out about when I expected.
You mentioned software, and one big challenge in HPC in general has always been the tug of war between maximum performance at any cost and increasingly the maintainability and productivity and the portability of applications. And I know there was a lot of focus on software for the Exascale program. What is your perspective on that? And I know you have had research projects that are aligned with that desire.
Well, I think it's really been a really important part of the Exascale computing project that it has a significant software technology piece of that sits between all of these innovative applications and then the innovative hardware. And that software is really what provides the glue in the project. And as you said, one of the challenges we've often had in high performance computing is making sure that software written for one machine can be used on another. And I think a lot of the tools that have been developed, these software frameworks and so on, that have been developed as part of both the software technologies program and the co-design centers, part of the Exascale computing project, are really designed to make it easier to move the different applications from one platform to another.
It's that whole ethos, I guess, is the word, capable exascale. So they really were very far off of being a stunt machine, if you will, just getting to a benchmark, but really having practical application, which I have to think at this scale just is really impressive.
Absolutely. No, I think it's really, and as I said, I think the breadth of application capabilities is also something I think is really unique to this Exascale program relative to even other previous US programs in high end computing, but also internationally. That there's just enormous breadth and a mixture of, as I said, traditional HPC applications and really completely new ones.
Right. One thing I wanted to ask, and I want to come back to the applications again, but these big projects, getting them funded, getting them shepherded through multiple years and securing the funds and tracking them, these just keep getting harder. And this is, of course, with your current role, how do you handle all of that? That's a really big problem, right?
Yeah, it's really important that the research community has confidence in their ability to get funding long term for the kinds of problems that they're working on. Otherwise, people won't want to work on these problems, even if it's really exciting for in the next few years to work on one of these applications, for example, or one of the software platforms. If there's no longevity in a career, then why would people want to work in one of these areas? So I think that one of the things that the DOE labs have been especially important in is giving people exciting scientific problems to work on, typically in teams that involve cross-disciplinary researchers, so people that are experts in an application area, whether it's physics or biology or chemistry or materials, and then applied mathematicians, computer scientists, and even within the computer science, people that really run the gamut from hardware experts to software and algorithms experts. So I think that provides a really exciting opportunity for people to work on these problems, but they also need to feel, I mean, people have careers and families and mortgages and things that they need to
Mhm.
worry about. And so providing stability for people is also a really important part of this, the whole HPC program.
And there's really increasing competition with the private industry that has renewed appreciation for the skill set of HPC folks.
Absolutely. Never more than I would say now, when the recognition is that machine learning has really become so powerful as a tool because it combines very large scale computing capabilities with very large scale data sets. And if you look for where the expertise traditionally has been and how do you take advantage of very large scale and fast computer hardware, it's been in the DOE labs. And so I think that, and I don't want to play the fact that there's certainly many university researchers as well that have worked on that. But the labs have really played a unique role in, as I said, putting together these teams that they don't just build a tool, but they sustain it over many years and
Mm.
modify it and extend it to work on new application problems and new hardware.
That's a really good point. So, actually, this is a good segue into your current role as Vice Chancellor for Research at one of the top academic institutions in the world. And Berkeley continues to show up in the top 10, if not the top 5, and has such a tremendously fine reputation and impact. So, the flip side of that is that how competitive is it to retain that kind of leadership? And especially as a public institution, love to get some color on that.
It's certainly a challenge. There is competition also across the universities as well as with industry, as you've pointed out, for talent. And that's faculty talent. It is also attracting graduate students and postdocs to work on research problems and training a very large number of undergraduates, which we certainly do at UC Berkeley, but also then attracting those undergraduates also to consider working in research. So it is very challenging to provide people with the latest resources and infrastructure they need to do research, whether it's supercomputers or advanced imaging technologies or advanced particle accelerator technologies, which of
Mm.
course we tend to go internationally for some of those. But there are different strategies for different science areas in terms of what kind of infrastructure is needed and how that is put together as a community.
I want to raise one topic. I'm just curious though, in the HPC community, there's lots of talk about the need for greater diversity. And I'm just curious at your
Mm.
level and what you're seeing. Are you seeing more women and people of color coming into undergraduate programs where they're on a track into people who would be in the HPC community? Are you seeing any progress at that level?
Interestingly, what we are seeing is a lot of interest in more of a data science area. So when you're looking at
Mhm.
data intensive applications, and I think that's because some of these data intensive problems, have a much broader spectrum beyond modeling and simulation, and they include problems in social sciences and law and economics, and where a lot of the modeling and simulation problems that have traditionally been equated with HPC are in science and engineering. But anyway, there's a broader spectrum of problems that include data intensive science. The fastest growing major right now at Berkeley is our data science major, and that is much more diverse than our computer science major has been and is today. So we're seeing a lot of that changing diversity in terms of interest. But the other thing that's interesting to me, and this is anecdotal, but it's based on just sort of talking with graduate students in the computing sciences area broadly, so including applied math and statistics and things, as well as computer science itself, that I think there's a growing interest in working on societal problems, that is, problems that will have broad impact. And that I think will draw a broader spectrum of students into these disciplines. Every semester, I have for many years given a lecture in our introductory computer science course. So this is a course for non-majors, and it's really just an introduction to computing and computing concepts, abstraction, and things like that. I give a lecture on how to save the world with computing, which is maybe a little bit of an
Awesome.
exaggeration, but I talk about climate change and the importance of high performance computing, modeling, and simulation, and really our understanding of climate, and also looking at health and how understanding of the human body and how it works and how different medical devices might be and what their benefit would be is also something that has benefited from computing. I can tell you that just again, anecdotally, the students that came up and talked to me after that lecture last week was a very diverse group of students.
That's excellent.
Would you mind just giving us that lecture right now? I'd be really, no, I'm joking. But I have to say, really, I guess what we're talking about here is HPC AI, joined at the hip when you get into data science and data scientists. But it's great to hear, Kathy.
Yeah, and AI gets bandied about now to the point that I'm not sure it has
Yeah,
its original meaning, but I
yeah.
agree that it really is about incorporating data and very large data into problems. And of course, then machine learning brings in this issue of doing, using these kinds of new algorithms that are really learning models from data as opposed to models that we write down as a set of equations in a, physics text or something.
So, speaking of saving the world with computation, how do you see the impact of digitization in general? I remember many years ago we had e-science as a thread, and it was not just the computational science and areas that lent themselves, but also farther afield, things like social sciences or agriculture and such. How do you see that across the vast array of research that happens at Berkeley and beyond?
Well, we see computing and data science, so those broad to include things like artificial intelligence, machine learning, algorithms into that as something that is really of interest to almost every discipline now across campus. And I certainly don't want to say that every researcher is using it, but there's typically somebody in each department, in each field that is looking at it. And sometimes it is quite dominant. And even if it wasn't, let's say, 10 or 15 years ago. So we're really seeing it much more broadly in the social sciences and even in the humanities and arts in a way that was not, as I said, not the traditional sort of view of what HPC applications look like.
Yeah, no, I remember actually, you reminded me, I was at Cornell many years ago, and one of the biggest matrix algebra problems came out of animal science because they had just giant matrices, observing things in the field, etc. So that's really good. I wanted to say, is there an area of focus, a school, a department that you wished existed at Berkeley that doesn't yet?
Well, it's funny you should ask. So there is a proposal for a new college, and it's called the College of Computing, Data Science, and Society. And actually, when I stepped down from my Lawrence Berkeley Lab position and came back to the campus, I worked for 2 years with the associate provost for that, what's now currently a division of Computing, Data Science, and Society, and that's Jennifer Chase, and worked with her and a team of people to help develop a proposal for that organization to become a college. And it'll be the first new college at Berkeley in 50 years. I think it's on track to become a new college, and it's very exciting to see that come together. If I were to say kind of the three words that we talk about with related to that college is foundations of computing. So that goes from everything from algorithms down to hardware, applications of computing. So we're very familiar with that in HPC. I think it's something that I brought in. That perspective is the applications oriented focus, and then implications. And that's something that I would say the HPC community has not traditionally focused on and perhaps didn't feel the need to focus on. But as we move computing and algorithmic techniques into social sciences, and you really need to think about what are the implications of automating something, what are the implications of using computation or algorithmic methods for making decisions about things, and so on.
That's brilliant. I'm really happy to hear that. And especially the word society and the implications, the formulation you just put forward is really excellent. So, rooting for that one.
Great.
As you mentioned, one of the implications, in fact, is the impact on policy. And HPC, given its prominent position, can and should impact policy, and it does. And maybe a good hard question is, should we worry about the health of open global scientific collaboration that has been around for several hundred years now to propel science in the face of geopolitical challenges and the global fragmentation that we're observing these days?
Well, let me start with the question of the role of computing in policy. And I think it is very important. I was at a meeting with Jennifer Chase, the associate provost for this new division of Computing, Data Science, and Society, and a group of faculty from across campus talking about AI and policy and how those fit together. And there are really two aspects of it that people in the room were interested. One is, how can you use AI, and I'm using that term as many people do today very broadly. How can you use it to inform policy or to make policy? But also, how do you regulate AI? And so there's kind of the flip side of that. And one of the things we talked about is what does it mean from a legal perspective for an algorithm to be fair? And I think in those of us who come from the technology space, think about fairness in algorithms as a technical question, but it also can be a legal question. And so putting those together is something that I think is going to be very important, exciting intellectually, but really critical in terms of how we make sure that technology is doing something that we think will overall benefit society.
You're referring there to bias, of course. And is bias a big concern for you? Well, I guess it is for everybody, or should be. But do you also move toward concern about automation, the automation of livelihoods that employs millions of people, and what we do about that when robotics and machine learning and machine intelligence really kicks in?
Absolutely. And we also at this meeting talked about that automation and job displacement, job replacement. And so somebody was explaining that there are different aspects of how technology can either replace or require new types of jobs. And then how do you ensure that there's the proper kind of training programs if the jobs are going to be replaced with a different kind? And so there are very complex issues there. And I think that, the economists here at Berkeley are also looking at those kinds of questions related to technology, as I think many people are around the world.
I think this is huge, and I'm really delighted that this is a topic of conversation with institutions such as yours who are able to distill it and provide sound advice, because I just think that this could be highly disruptive if it's not managed properly.
Yeah, it's one of the things that I find especially exciting about my position here at Berkeley is being able to connect people. I sometimes refer to myself as a matchmaker and translator because I'm trying to bring together expertise in, whether it's computer science or physics or engineering with, say, somebody who's an expert on economics or, social science or other disciplines like that to really have a unique perspective on how you solve some of these big societal problems.
Right on.
Yeah, I agree with Shane. I'm very glad to hear an institution like UC Berkeley is discussing, thinking about these issues because the industry itself, the vendor community is just rushing forward willy nilly as fast as they can, naturally. That's their role. But sometimes I wonder if enough thought is going into the foundations of how we're going to handle the changes that are coming up. So that's great to hear.
Now, let's come back to the details of things, because one of the things I really enjoy talking to the few people such as yourself who have a breadth from the details of a technology all the way to social and public policy is that you could actually stretch that rubber band so much. So let's start with, again, UC Berkeley, because I think its impact on computer science, electrical engineering continues to be enormous, not just with the globally famous projects like Berkeley Unix in the old days, and then Apache Spark in a little bit more recent, and even more recent than that, RISC-V. But there are also several examples that are near and dear to yourself and are really exciting. So I want to start with PGAS because I know that's something that you led, and every letter in that acronym is really pretty cool. So could we spend a little bit of time on that?
Yeah, so let me say a little bit about this idea of partitioned global address space languages and programming models and what that really means. To me, it's not about a specific language, and I've certainly worked on a number of those as well as the compilers associated with them. It's really about how do you think algorithmically about the problem you're trying to solve. So let me give an example that comes up in the genomics application that we're working on. You take in all of this raw sequence data, terabytes of sequence data, and you're trying to do some analysis to figure out where the errors are because the sequencers inject errors into that data. So one of the things that we do is we chop it into little fixed length pieces, and then we kind of want to sort them somehow. Well, we put them in a big hash table. What that hash table looks like and what it means to construct it is this data is spread out over, let's say, 1,000 nodes of the frontier system. And one of those, a processor, a core on one of those nodes, has got some data that needs to go into a piece of the table that's sitting on another processor. So in this PGAS model, that processor can directly kind of read or write the memory of that other processor and stick it into a data structure on the other side. And that leads to a different sort of algorithm than if you said, oh, the only thing that processor can do is talk to another processor by doing, say, a send receive, or all the processors can get together and do a reduction or a broadcast. And those are very powerful primitives as well, and really appropriate for a lot of applications. But in this case, where you're saying the processor that owns that piece of the table, to personify it, has no idea that some other processor is trying to insert into its piece of the table. So it can't really
Mm.
implement that as a two-sided communication operation. So, and what I've seen, and this is through a collaboration in the Exabiome project with people like Aydin Bulic, who thinks about things somewhat differently in more of a linear algebra perspective, where can you turn this into a problem where you're multiplying by matrices? Well, turns out you can, and that will lead to a different sort of implementation, different sort of parallel algorithms, different parallelization strategies. But to me, that PGAS idea is allowing people to think about algorithms that allow one processor to directly manipulate a data structure that is owned by another processor.
That's brilliant. Exabiome has come up a couple of times in our conversation. Let's drill down on that. That sounds really interesting. And also, it seems like relevant to just the digitization of that process in recent years and the quantified self and the work that Larry Smart was doing. Are they all related? Tell us a little bit more about that.
Well, absolutely. I think that being able to understand the genomes around us, and of course, the original sequencing of the human genome really required an enormous computational system, but also innovations to figure out how you're going to analyze that raw sequencing data. And today, those problems continue. What we realized early on, even really before the Exabiome project started, was that most of the production codes for analyzing sequence data and specifically environmental genomes was really built for shared memory machines. And that
Ah,
pretty fundamentally limits what you can do. So, you can get up to maybe a terabyte, except that, by the way, in the middle of the computation, the data structures sort of blow up by about a factor of 10. So probably a terabyte, even on the largest shared memory machine you could get, is going to be pretty close to your limit. And so what we did was to say, well, if you think about it from this partition global address space perspective, can you take those shared memory algorithms and run them on HPC systems with distributed memory? And the answer is yes, you can. And it leads to non-traditional sorts of application codes. Now we've got a couple of different genome assemblers actually built on different models. One of them is built on this PGAS model, the partition global address space
mhm,
model. And the other one is built on more of a sparse matrix linear algebra model, or where you're doing sparse matrix multiplies. And so that to me has been the most interesting thing as a computer scientist about the
mhm,
project, is being able to
mhm,
see these two very different approaches being successful in different ways. But now, at least with the code that's been around longer called MetaHitmer, that is able to now assemble multi-terabyte data sets across these systems. And we recently assembled 30 terabytes of an environmental data set called Terra Oceans. It's really fascinating to me, science
mhm,
project of people that sailed around the world and collected data from all of the oceans of the world, collected water from all those, and then sequenced them. And what that means is you've got microbial communities, little microbes that live in each scoop of water that gets sequenced. And now the problem of analyzing that data, I refer to it as like putting together a puzzle. And
mhm,
that's true with any sequencing data, because the sequencers chop it up. And as I said, they inject errors into it. So you've got to figure out which pieces are good and which pieces are bad, and then put all your puzzle pieces together. The human genome, we now have the cover of the puzzle box, if you will, because we know what the human genome roughly looks like, even though there are variations between each individual. So you can look at that cover and say, oh, this piece probably goes here in a particular place in the human genome. But in a environmental genome, you have two problems. One is
mhm,
some of those genomes we've never seen before. We haven't sequenced them. We haven't been able to even grow them in a laboratory environment in isolation. So we don't know what they look like. And so you don't have the cover of the puzzle box to use as a crutch. But the other problem is the genomes are all mixed together. So now imagine that somebody took say 150 puzzles and dumped all the pieces together on the floor, took all the
Oh,
covers away. Now you've got to put together those puzzles. And that's the computational problem we're working on.
nice. Nice.
Well, good luck with that. Okay.
Well, maybe that's why we need systems even bigger than Exascale. And maybe
Yeah.
that's a good segue into what's next. What do are we, clearly we're not good for a while. I thought for a moment that maybe with Exascale, we can just sit tight for a while, but doesn't look like it, right?
Oh, I think that the interesting thing about working with scientists, researchers broadly is that they always have new ideas of what they can do and problems they can solve if they have a more powerful instrument, including a more powerful computer. And one of the things that I often say is that it's really hard sometimes to get people to think exponentially. That is, what would you do with a system that was 1,000 times more powerful than the system that you have access to today? So that can be a challenging conversation to have because you're looking about 10, 15 years out into the future typically. But on the other hand, I think in computer science or in computing broadly, we're sort of in a different domain where we're so used to the idea that if you wait 10 years, you're going to get something that is about 1,000 times more powerful. That if that stops, that is going to be as disruptive as the idea that you're going to have something much more powerful. So it's really, this is true throughout computer science as well as other disciplines. They're used to having computers become more powerful, and I mean that in the broadest sense, not just
Mm-hmm.
10 or 100 or 1,000 times more floating point operations per second, but more memory, smaller scale, less weight, more cost effective, just all of those things that have led to the explosion in the use of computing.
Are you somebody who has kind of a bias or a favorite aspect of these systems, whether it's the processing power or the memory size, or do you think in those terms?
I think I've always tried to think about systems that are balanced. And when I was the director of the NERSC facility, National Energy Research Scientific Computing Facility at Lawrence Berkeley National Lab, that was really what we tried to do in general. And it's a hard problem because you're trying to balance a system for all of the scientific users that are going to use that system. And somebody like me who's doing genomics applications, by the way, we don't use floating point. So, already you can see that that's a very different workload than most of the other users that are on those systems. So you're trying to figure out how to design a system in which you've got enough memory and enough memory bandwidth to balance the amount of computing that you have. And it does depend on the application needs, what that workload is going to look like. And so I really try to think of things as trying to keep them balanced. The problem is that the costs are not balanced. So the problem of getting 100 times more memory bandwidth may be much harder than getting 100 times more floating point operations. And so that
Yeah.
just means that there can be a different question, which is, well, if you could have 100 times more floating point operations or twice as much memory bandwidth, then which one would you choose, right? So it's not between kind of equal amounts of both, but the costs are very different. And by cost, I mean not just dollars, but it could be energy, area, size, weight, all kinds of things.
Just looking back over, say, the last 10, 12 years of these leadership class systems and HPC, higher end HPC in general, my sense is that more and more balance is coming into the picture compared to, again, 10 to 12 years ago. Am I right in saying that?
I'm not sure. I think that I would say that in recent years, it's been easier still to get more computing performance than to get more memory bandwidth. So I would say
Okay.
that balance has not been as easy to maintain. But I do think that there are some really exciting technologies coming in the memory area and communications area that will lead to better balance of systems. And so I'm very excited about the future. That said, we've got big challenges ahead as we approach the end of Moore's law scaling and we're reaching atomic scales in terms of the transistors. And that's really going to have I think, a very significant impact. And I think it will require that we have much more thoughtful conversations even between hardware designers and application developers and the applied mathematicians and computer scientists in between, thinking about how you're going to map those problems or different problems or different formulations of those problems onto the machines.
Perfectly said. So as we look towards zettascale, if it manifests itself like that, and all of these new technologies that are coming. And if you look at the spectrum from digital to analog and from classical physics to quantum physics, and maybe biological computing has also been mentioned, and how much information I can put into DNA. How do you see about these new technologies playing a role in computing infrastructure of the future?
Well, I'm very excited about these alternate technologies. I mean, you look at something like quantum computation, I think it's just allows for fundamentally different kinds of problem formulations. On the other hand, I think it's important that we recognize that it doesn't replace general purpose computing, digital computing that we have today. And so I think it may allow us to solve problems in, say, material science, chemistry, high energy physics, cryptography that we can't solve today with classical computers. But there will still be, I think, a really important need for faster classical computers, even along with some of this other very exciting technology, which may give us different capabilities.
I've been very interested in the RFI put out by DOE in late June about their strategic thinking for the next round of leadership computing systems. And they're moving away from this monolithic idea and more toward an aggregation, I guess, of compute resources as the next wave beyond exascale. I don't know if they're saying that'll get us to zettascale, but I'm curious if I wouldn't be surprised if you were part of the strategic thinking or contributed to it. But do you have thoughts on that RFI?
Well, let me talk about what I see as one of the future directions that I think DOE has to go in, and I think there's a lot of interest in this. We call it. There's different terminology used by different people across the lab complex, but I think that it's not just about tying together computing systems, but tying them together with the major user facilities. So, what is DOE, the Department of Energy, known for, especially at the labs? And they're known for running these really critical user facilities that are used by thousands of university researchers, graduate students, postdocs, faculty, as well as lab scientists. So this is a really important part of the kind of fabric of how the US supports its scientific research enterprise. But those instruments are starting, if you look at something like the light sources, the sequencers, the telescopes, they are producing so much data that the scientists in those disciplines recognize that they can no longer solve their own computing problems. So it used to be that you could take your data on a memory stick and then go bring it back home, and maybe you had a little server, maybe you had your laptop, you could do your analysis, maybe you're using R, something like that. It's completely different today. And the genomics example that we've talked about is just one narrow example of how people cannot solve these problems on personal laptops, and they really need to think about using high performance computers for them, perhaps the leading edge systems beyond exascale. And that's because data is going to stream from the instruments into the supercomputers, and that you want feedback on it. You want the supercomputer, it may be doing some amount of simulation, this sort of digital twin idea, and then using that to control the instrument or provide feedback on what the scientists should be looking at and how to improve the experience of that researcher.
Okay, so you're a vote for this idea. It sounds like, yeah,
Yes,
you're in favor.
yes,
Okay,
if that wasn't clear, I'm all for it. Yeah.
very good.
No,
All
it
right.
makes perfect sense. It also kind of goes against the balance, so to say, because with specialization and a customization of different classes of computing, I don't know what that does to balance, maybe within a discipline, but not across.
Well, that's really the interesting question, isn't it? Is whether when you specialize a computer chip, for example, which is probably going to be one of the main techniques that we have for continuing to get performance in the short term, that is that only useful then for a one algorithm or one scientific domain? You look at something like machine learning, I would say, well, okay, maybe it's only good for convolutional neural nets, but they come up all over the place in image processing. And if you generalize it somewhat, it goes beyond images and beyond, for example, 2 dimensions into 3 dimensions, which, by the way, might change the hardware somewhat, but that might still be a very general tool for things. I think that this gets back to something I've worked on for many years with many different researchers, which we call motifs of parallel computing. So what are the patterns
Mm,
that come up over and over again, often across different disciplines? So it's really not about the scientific domain. It's about kind of what are the algorithmic nuggets that are going to get used over and over again that can be encoded into hardware.
Nice.
exactly. Yeah, yeah. So that almost is like a math library, that those would be the meta constructs that would tend to repeat. Is that along the same thought lines?
Yeah, a math library, typically you would have higher level algorithms, but if you look at something like LAPACK or ScalaPack, those are built on matrix multiply, matrix vector multiply, and a relatively small number of basic kernels, in which a lot of those can be
Mm,
highly tailored to the hardware and really, really optimized very effectively. And so when you're solving an eigenvalue problem, you don't necessarily have to worry about, what the hardware is doing and how to take advantage of that, as long as you're building on these highly optimized building blocks. However, we also know that sometimes you do really want to look at the higher level algorithm, because sometimes you can reformulate it in a way that'll be a better match to the hardware.
right on. So in our conversation, you've touched on computer science, on electronics, on natural sciences. And I think the fact that all of those topics can be discussed in one sitting with one person is a very important piece of the puzzle. What can we do to educate the next generation such that they have this kind of a diversity of expertise? And, maybe the specialization also within the disciplines is something that can be addressed and have some more peripheral vision. Because, I talk to computer scientists who really don't know much about an eigenvalue or a basis set, or, how fluid dynamics might work. Would you comment on that?
Yeah, I think that there have been programs like the computer science graduate program in the Department of Energy to help train graduate students who have this broader perspective about computing, computer science, mathematics, and applications. And I think that is very important. I think it's also going to continue to be a really important part of what we do at both universities and the national labs in terms of postdoc training. So if you think of a PhD thesis as becoming the world's expert on a very, very specific topic, you're learning more and more about kind of less and less until you are the world's expert on that one thing. And then I was speaking to a group of postdocs here at Berkeley just a few weeks ago, and I said, in your postdoc experience, you really want to step back from that and think about, okay, what do I want to do in my career? What other training, what other education opportunities do I need in order to be successful in that? Taking that really fundamental expertise that I have and then applying it in whatever area you're interested in. So I think that will be important that we have that broader perspective.
Brilliant. Thank you.
All right, Kathy, thanks so much for joining us today. We'll have you as a guest sometime in the future. It's been a real pleasure.
Great. Thank you very much.
Certainly has been. Thank you.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.